Hi guys, welcome to chapter 22, section A. We're going to talk about the sun today. Okay, so we're familiar with the sun because that's where our light and our heat comes from. That's what keeps the atmosphere warm enough for us to live and grow plants in. But there's a lot more to it than that. Okay, it's huge, it's massive. The sun is massive, it's a huge star. It's 1.4 million kilometers in diameter. So the distance across the whole sun is about 109 times the diameter of the Earth, 1.4 million kilometers. The reason it doesn't look huge in the sky, I mean, it's a lot bigger than the other stars because those are so far away. But the reason it's even as small as it is because it's 150 million kilometers away from the Earth. Now, that's a really big number. And so astronomers have come up with the astronomical unit to kind of refer to that distance. So one astronomical unit is the distance from the Earth to the sun. And they use that to talk about things that are even farther away. You know, if something is 50 astronomical units away, that means it's 50 times farther than the sun is from the Earth. Okay. The sun is not solid, it is gas, mostly gas. And some of that gas actually gets hot enough and becomes charged to become plasma, which is another state of matter. Okay. So the sun's energy, most of the energy that leaves the sun leaves as the form of an electromagnetic wave. Light is included in that. But if you look at this diagram here, okay, what we actually see as light is a very narrow range. The overall spectrum of the electromagnetic waves is way beyond that. We've got, radio waves out here and gamma waves and X-rays and microwaves and all these other things that we can't see but are still forms of energy coming from the sun, okay, just different wavelengths. The visible spectrum is only between 390 nanometers for the violet and blue side of things, up to 700 nanometers for the red light. Okay, so when we look outside, what we see is within that visible spectrum, and the different colors we see is within that spectrum. Okay, when all those wavelengths combine together, that's like white light. That's the sunlight. Okay, and we only see things because the sunlight is bouncing off of those things. Okay, if we go shorter than that visible spectrum, okay, so a shorter wavelength over there, that's called ultraviolet. Okay, it's not visible. It's still energy, and it still gets to us. It's a form of radiation, actually, and that's what causes sunburns. The reason sunburns are dangerous and the reason UV rays are kind of dangerous is because that radiation can actually damage our DNA and cause skin cancer. On the other side, so now longer than the visible spectrum, is called infrared. We can't see infrared, but we can feel it as heat. We can use instruments like infrared cameras or infrared goggles that can kind of translate those electromagnetic waves into a visible image, but we cannot see that with our eyes. Okay. All right, what is the Earth, so the sun made of? More than 98%, almost like 99% of the sun is hydrogen and helium. Okay. And those two things are reacting together, and that's where the energy is coming from. But there's also at least 79 other elements in some trace amount within the sun, okay? But it is a gas. So the structure of the sun, scientists, are conjecturing this, they're predicting this, they're planning this based on observations, based on the measurements they can take, but obviously nobody's ever been to the sun, okay? So the core of the sun is it could be about 15 million degrees Celsius, and that's where all the energy is coming from. Okay, so this process of nuclear fusion, what's happening is the atoms of hydrogen are kind of combining, the protons and electrons and things are combining to make atoms of helium, and that process releases a huge amount of energy, nuclear fusion. Okay, outside of the core, we get into the radiative zone. So that's like this part right here, okay? And it's so hot and so dense, and there's so much pressure that the electromagnetic waves move actually very slowly. So it's kind of difficult for them to get out to the outer layers, okay? Plus, because of that nuclear fusion going on, as the electromagnetic waves are coming off, they're kind of being trapped by other atoms in there. And so it takes a while for those waves to get out to the next layer. which is called the convective zone. Okay, so really low density plasma kind of rises up, and then the higher density plasma sinks down, and it forms convection currents, kind of the same thing that we see in the mantle. Okay, both of them are incredibly hot, but there's enough of a density change in that plasma that it does create that current out there. And then finally, the surface of the sun, this is the visible surface of the sun, is called the photosphere. And it ranges in temperature from 4,800 to 6,000 degrees Celsius. And remember, it's not a solid, it's still a fluid. Those gases are making up that surface, okay? So the sun is so dense, and especially the core, there's huge amounts of gravity, okay? And so that's what keeps it in that shape. The gas won't escape very easily. It's all kind of condensed together in a ball because of the gravity. All right. Now, there is an atmosphere outside of the sun. It's called the chromosphere. The lower part of the atmosphere it goes to about 2,000 kilometers beyond the photosphere, the surface there, okay? It gets up to 20,000 degrees Celsius, okay? Now, the edge of the chromosphere, like kind of the very outer part of that atmosphere, is called the corona, which means crown, because it kind of makes this jaggedy shape. It's not a perfect ring around the sun, okay? It is only visible during an eclipse, okay? There's special instruments that can detect it partly, but it's really only visible during an eclipse. So the white part that you see on that picture is the corona, okay? And it's millions of degrees in temperature. And it's kind of that electromagnetic energy starting to then escape the atmosphere, okay? So the sun has all kinds of funky stuff going on, these different types of activity. There could be these prominences, which are like these kind of loops of plasma, kind of, firecracker-ish, kind of streaming away from the sun, but then it falls right back to the surface. Those are prominences. Solar wind we talked about in a previous chapter, and that's when the charged particles, that plasma, can actually leave the corona and go into space. And that extends in all directions. When it gets to the Earth, that can be really bad for us, but fortunately the Earth has that magnetic field that protects us from the radiation that the solar winds bring. Sunspots are what you see in this picture there. They're darker spots on the sun, and they change. They're not permanent spots. And they're slightly cooler spots on the photosphere, and so they look a little bit darker. And there's kind of seasons of sunspots. There's some periods that have more sunspots than others, and they can actually have an effect on our climate, okay? Solar flares we also talked about. This is basically just explosions of the sun's matter leaving, these charged particles leaving the sun in higher amounts, bringing radiation with it. These are more common when the sunspots are more active, okay? Those solar flares, when they hit our magnetic field, that's what causes the aurora borealis in the north and the aurora australis in the southern hemisphere, okay? Wow, that's it. That's the sun. We're going to look at the sun carefully in class.